Hello AP Calculus students, Mr. Record here. We're going to take a look at a video which is going to finally introduce this concept of finding the area so that we can gradually segue into the setup of the definite integral. But before we do that, I want to provide a little bit of motivation behind why we want to do such a thing in it. And actually can be looked at in a little bit of a historical context here. Say you wanted to take a look at the area of a circle, and several thousands of years ago, the ancient Greeks were very interested in doing just such a thing. But during that particular time, the discovery of pi had yet to come around on the horizon, and the Greeks were just pretty much handcuffed to being able to find the areas of simpler shapes. They knew how to find the area of a rectangle and a square, and they had built their inventory of formulas to include the triangle as well. So if we wanted to find the area of a circle, we could think about dividing that circle into separate shapes of areas which we did know how to find, like the triangle. So if you look at circle 1, that's divided into, I believe, 6 triangles, or 7 triangles, 3, 4, 5, 6, 7. And then if you take a look at circle 2, which divides into 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 triangles, it's probably pretty clear which one would give a little bit better estimate of the area of the entire circle if we just included the triangles only. And that certainly would be circle 2. And then you could come across the conclusion that if you were to divide the circle into many, many more triangles beyond 12, you would probably be able to calculate an area of the circle that's even more accurate. So the question sort of becomes just, how far we could take this. How many triangles could we conceivably use? Could we use, say, an infinite number of triangles? So that's sort of the motivation behind setting the idea of area up as far as calculus is concerned. And we're going to first explore an example here that's concerned about finding a left endpoint and a right endpoint sum, which if I go back just a slide here, we use the topic uppers and lower sums. And while I'm not going to worry a whole lot about that particular vernacular with this video, in a later video we'll go into more detail about that, but I still want to point out which of these particular approaches would provide for an upper sum and which would provide for a lower sum. So if we look at our example, this is a very typical opening example about finding area using rectangular subintervals. We would have the function f of x equaling negative x squared plus 5 graphed on the interval 0 to 2. And we're to find the two approximations of the area that lies between that function, the x-axis, the vertical lines x equals 0 and x equal 2, using those 5 subintervals that are rectangles. And we're asked to draw in the representative rectangles for each approximation. So the first thing that I want to do is to partition this x-axis into those particular subintervals. And you can see that the y-axis is already taken care of it for us. They're very, very small numbers. And in this particular case, I want to go ahead and use, for the x-axis, 2 as the very far right interval. So we have to think about exactly how wide each of these subintervals is going to be. So if you think about this for a little bit and you say, well, if I'm going to go from 0 to 2 and I'm going to divide that into 5 separate shapes, I would take the entire length of this distance from 0 to 2, divide by 5, and of course come up with 2/5. And that's what we have right here. 2/5 would be the length of each subinterval. So your first partition would be right at the 2/5. 2/5 beyond that would take us to 4/5. 2/5 beyond him would be 6/5. 2 more fifths would be 8/5. And then if I go 2 more fifths beyond 8/5, I would have 10/5, which of course is our 2. Now the next thing that I want to do is I want to partition this shape by drawing some vertical strips from these values up to the curve. And I want to pause the video for just a moment so that I can do that a little bit quicker. Okay, now that I've done that, is that when we build rectangles, these rectangles are going to be defined by having a height positioned at the right side. Now, if you look at these shapes, of which there are 5, there is definitely no arguing the fact that these 5 shapes are not rectangles. They have the curved tops to them, which obviously doesn't meet the criteria of a rectangle. But if we were to go into this first shape and take a look at the right edge of it and find out where that right edge meets the graph, and I'm going to define that point there, we simply would cap off this rectangle by drawing a horizontal line across from that particular point. We'll do the same thing with the second shape by reaching the curve and capping it off. Now you'll notice that when we cap these off, we're actually drawing a line segment towards the left. And I think sometimes that gets students confused. We draw the line segment toward the left, but we're drawing that line segment from the right endpoint. So this is going to constitute a right side endpoint approach. And if I continue to do that, you'll see that for this particular shape, the right endpoint is always going to force us to draw that segment to the left. And I think the reason beyond anything else is the fact that this curve is decreasing, and that's going to make that happen. Now, once that is taken care of, it would be and we are going to look at the fact that the area of each of these rectangles is simply going to be a matter of finding the length times the width. Now, the width of rectangles is very consistent. In other words, we can see that 2/5 is very equally used with all 5 particular shapes. So what I'm going to suggest that we do is to take that 2/5 and factor that out in front of an expression that will take the sum of all of the heights. You don't have to do that, but it is definitely going to save a lot of time in having to write 2/5 on 5 different occasions. Now, to find the height of each of these rectangles, we're just going to take one of them at a time, beginning with this 2/5, and physically plug the 2/5 in for the function f, in for the x value, I should say, for the function f. So we'll have f of 2/5, which would essentially be that value that I'm denoting right there. I'm not going to do this for every one, but I think you'll get the idea by marking it just one time. And then we continue that for the other places. F of 4/5, followed up with f of 6/5, and so on. And we finish up with the f of 2. Now, the only thing that needs to be done is to evaluate all 5 of these particular functions and these function values, and then do the arithmetic. And because of the nature of the fractions and so forth, we'll rely on technology to do that. Now, to evaluate these particular guys, I'm going to go ahead and use a TI Inspire calculator, but if you're watching this video, say outside of Avon High School, it really doesn't matter what technology that you're using. Any kind of a calculator, whether it's a graphing calculator or a scientific calculator, is going to get the job done for you. But to do this on the TI Inspire, probably the most efficient way would be to first of all define that function f of x. So we're going to go ahead and type in f of x, and we'll use the notation to define, which is the control math template. You can see how that would place the colon equals onto the screen. And then we use negative x squared plus 5, of course, which is our function. And if we hit enter, we get the word done, which means that it understands what we're doing. And then at this point, what you could do, a variety of things. You know, one approach would be to just simply enter f of, and notice the f is dark so it understands what the function is, and we could say do something like that. The problem with that, that's going to cause us to kind of have to use a lot of excessive typing. So what I think I'm going to suggest instead is to say, well, okay, well, let's figure out what this f of x is, and then I'm going to use the such that symbol, which can be found in the control equal option, the 6th option available there, the vertical bar. And then I can say x is equivalent to, and then if you're going to follow that up with more than one value, say a string of values, then you're going to want to use the braces, which are found by hitting the control right parenthesis. And it's really important that you use the braces. If you use brackets or parentheses, this function will not work. So we're going to go ahead and use, oops, let's get rid of that pair of equal signs. We're going to go ahead and use a fraction template and throw in 2/5. And then we just simply need to separate each of the values with a comma. So we throw our comma in there, and then we just pretty much repeat the process for 4/5 and so on. Like I said, not the prettiest values in the world. We kind of luck out here at the end for our 5th value just being 2. But when we hit enter, what we will get would be the values given to us in a respective order. So you can see how the 121/25 refers to the f of 2/5, like we had up in this top line. So I'm going to pause the video as I transfer those particular answers back to the main Smart Notebook page. And there we have our expression that would depict the unsimplified area using the right side endpoint. Now, while this answer is actually, by standards of the AP Calculus exam, acceptable, I want to go ahead and take it a step further and have us actually simplify it into a kind of a nice single fractional answer. And the way that you're going to want to do this is probably using your calculator in a very clever way. And again, I think the focus of the problem now becomes, you know, how to manipulate these massive numbers of ugly fractions. But I have a clever way to do this for the TI Inspire. So I'm going to keep that width of 2/5 out in front and just focus on what the sum of these 5 fractional values, these 4 fractions and 1, is going to be. So if I return to the Inspire, a really clever way I've discovered to do that involves doing a little cutting and pasting. So essentially, I want to take the 5 values in these braces. So to do that, I can just cursor up with the up arrow, and then I can use the shift button in conjunction with a right arrow. And you might have to kind of play around with this a little bit on your calculator to pull this off. But essentially what you're going to do is just highlight those 5 numbers. You don't want the braces to be included. Now you won't have any choice but to have the commas included, but I'll show you how we can take care of those. So you'll go ahead and hit Control C for control copy, just like you would on a PC. And then you want to go into that empty space down below. Once you're in that space, you'll use Control V for paste. But as you can see, you've got those commas which aren't going to be very helpful in terms of finding the sum. So just simply back cursor and then delete and insert an addition symbol in the place of each of the commas. And upon doing that, you will be able to hit enter, and then that will kind of spit out the final answer as a nice simplified improper fraction, 81/5. So we know that all of these terms multiply or add up to make 81/5, which means our final result, 162/25, is going to be pretty easy to find. 162/25 is the area of each of these 5 rectangles that are sort of inscribed within this curve -x²+5. Now, when you look at the left side endpoint approach, you might think, oh gosh, we got to do this whole thing all over again. Well, that's not necessarily true, because the bulk of so much of the work that you've done has been taken care of for you, and you may not have to manipulate the calculator nearly as much. But what you will have to do is partition this x-axis out much the same way, where we have 2/5, 4/5, 6/5, 8/5, and 2. Let's make that 6/5. Then again, I'm going to pause the video so that I can draw those vertical strips. And now it's very likely that we can see that a left side endpoint, much like the right side endpoint, is going to utilize some positions on the curve. And for our first rectangle, we're going to use the y-axis and where it beats the curve. And you can see how we will draw a segment moving to the right. So again, even though the name is the left side endpoint, you actually will draw your segments to the right from the left. And you can probably tell that these rectangles are going to lie somewhat outside of the region in which we were trying to find the area. So we have our 5 shapes as such. And then when it comes time to fashion our area expression, I'm going to use a subscript of L for left endpoint. Again, we see that 2/5 is our width. But the change that we now have in front of us is that the left endpoint that we're going to use for our very first rectangle is going to incorporate the x value of 0, where we did not have that before for our right side endpoint approach. And we will continue this same thought using the 2/5 and using the 4/5, the 6/5 and 8/5 as well. But as we move to the end of this shape, our 5th shape, we will not have to incorporate the 2 because the 8/5 served as the left endpoint. It's pretty much for the same reason why we did not have to incorporate f of 0 for the right endpoint. And as you can see, much of the work has already been done for us when we evaluated the right endpoint. Now, sure, we don't have f of 0, but we won't need a calculator to compute f of 0. We can just go up to this function here and let x be 0, and we, of course, get 5 for the result. But then we'll just use those next fractions that come down the line, 121/25 plus 109/25 plus 89/25. Finally, 61/25. I'll pause the video one last time to throw these results into the calculator, and then we'll wrap things up. Again, I could incorporate a little bit of a trick here and copy the values that I had previously and paste them on a new line, but I'm not going to use that 1 at the end, and I'm going to use a 5 at the beginning. I could put the 5 no matter, the front or the end, but I wanted to retain the order. So if I add all those up, I would have 101/5, And when I finish it up by multiplying through by 2/5, I would ultimately have 202. Let me get this correct. No, I stand corrected. I think I need to put 101 over 5 and not 101 over 25. So 202 over 25 ends up being our left endpoint approximation, whereas 162 over 25 was our right side approximation. Due to a little technical glitch, I was unfortunately unable to recover the graph. But what I wanted to point out here is that the value that we see on the right side of endpoint is certainly going to be less than the approximate area using the left side endpoint. So that probably seems, you know, pretty logical if you look at the sketches. But the big question remains is, what would be the actual area for the curve? Possibly something in between? Would it be exactly halfway between? Well, that's going to be a video that we're going to investigate. An idea in a little bit later video. But for right now, I think this pretty much takes care of the left side and right side endpoint approximations, and I certainly hope this helps.